Alright, this is day 4 of the first week. We are going to discuss chapter 2, describing distributions with numbers today. Yesterday we talked about chapter 1, which was describing distributions with graphs. Today, chapter 2, describing distributions with numbers. And I have posted this lecture note on Canvas. Make sure that you downloaded it and you are going to watch this video, and while watching the video, you can complete the points in the lecture note. And point number 1, give an intro statistics definition for the probability distributions. We kind of gave a very simple definition on the previous day, and today we are going to give a more complete definition for probability distributions. So on the first day, we said probability distributions are the things that describe the shape of your data. And it should also give you the probability. Those are the 2 points that we discussed under distributions definition for point number 1 of the class of yesterday. So today, let's generalize it a bit more to sound it more complete. Yesterday we said we can see fixed graphs only for quantitative data. Therefore, we actually say the distributions can be easily defined for quantitative data. So, at introstat level, I will define the distributions this way. The shapes of quantitative data. That's the first part of the definition. When I say shapes of the quantitative data, what are the shapes? The graphs. We said we have histogram and we have stem leaf plot, and you can come up with any other graphical representation as well for the quantitative data. If your histogram looks like this nice symmetric bell curve, then your stem leaf plot will also look like this nice symmetric bell curve. And if your histogram looks like, let's say, a rectangle shape, then your stem leaf plot will also look like a rectangle. No matter what your basic graph looks like, one of the graphs looks like, all the other graphs will similarly depict that same figure. The best graph out of all these existing possible graphs for quantitative variables is simply the histogram. So I will define distributions this way. Shape of the histogram. Shape of the histogram of, we say, the quantitative random variables. Shape of the histogram of any quantitative random variable. Now this is a bit more complete definition, but also this definition must include the probability statement. Well, what's the probability? Probability means always a number between 0 and 1, remember? Well, if you have taken any math class and if they talked about probability, probability can be seen as a number between 0 and 1. Remember that definition for probability at introstat level. Okay? Any number between 0 and 1 can be interpreted as a probability. Also, if you convert that into a percentage, it will be between 0% and 100%. Where 0% is equivalent to 0 and 100% is equivalent to 1. So any number between 0 and 1 can be represented as a probability. So, is there a way that I can scale down the histogram into represent a total area of 1 unit? Well, of course, I can do it easily. I can just divide the area of the histogram by its total area. Okay, so I will write it as this shape of a histogram of any quantitative random variable adjusted for the total area to be equal to 1. If the the total area is equal to 1 in your histogram, let's say this is my histogram. I have class intervals on the x-axis and frequency on the y-axis. So this is my histogram for some quantitative random variable. Let's say this is for temperature. So it may be from 0 to 100 degrees. Now I need this histogram to have a total area of 1 unit. Well, I can divide by the total frequency and make sure that this histogram, this total area under this curve is equal to 1. I can do some adjustment for that. Now after doing that, if I need to find, let's say, the temperature between 20 degrees and 70 degrees, all I have to do is to find this total area. Now that area will be equal to some number between 0 and 1 because the total area is equal to 1. In that case, area between any two points within this domain will be lesser than 1. So that's a good way to define a probability distribution. Well, this may not be the most perfect definition for a distribution. Of course, this is not the most perfect definition for a distribution, but this definition stands perfectly all right for intro statistics classes. So try to remember this definition for probability distributions. The shape of the histogram of any quantitative random variable adjusted for the total area to be equal to 1. Let's move on to the next point. Mathematics. Families of geometric shapes can be described by parametric equations. Do you agree or disagree? Explain. Now this is a little bit of a deviation from statistics discussion. Now I need to talk about families of specific graphs discussed in mathematics. The reason is, we said histogram is always a fixed shape for a given random variable. Now, can I come up with an equation for that? If I can come up with an equation, then I have an equation for the distributions. Equation for distributions means I can find probabilities using that equation quite easily. Well, it may be easy, it may be a little bit difficult when you deal with equations, but it's very clear that I can find the probabilities when I have the equation of my graph. So, when you have a fixed shape, will you always have an equation? Well, think about straight lines. In mathematics, we say y equals mx plus b represents a straight line. Say for example, y equals 2x plus 3. Now this is a straight line, right? This is a straight line. And y equals negative 5x plus 10. That's also a straight line. Now what are the parameters of this straight line? Well, x and y are variables. The variables will always be written as variables in your equations of whatever the geometric shape. In this case, a straight line. Then, what are the parameters? Well, m and b are parameters. For any specific value of the parameters, you have a specific graph of that family. Now, this is the family of straight lines. And like I said earlier, m and b are parameters. They are called parameters. X and y are called variables. Now these are examples. This is a straight line. Now this is also a straight line. So no matter what values the parameters take, when you substitute those values in this equation, you get a specific straight line. You will only get a straight line for different values of m and b. By changing m and b, you cannot change the overall family of the shape. So when you have a specific shape, you can always find an equation. So this is one example. Look at the circle. If your center is h, k, the coordinates, and if the radius is r, what's the equation of this circle? from college algebra, you must know x minus h squared plus y minus k squared equals r squared. Now x and y are variables. H, k and r are parameters. By changing different values of h, k and r, you can obtain different circles with different centers and different radii. X and y will always be in this equation. Now for example, x minus 3 squared plus y plus 2 squared equals 4 squared is a circle whose center at 3, negative 2 and radius is equal to 4. So likewise, by changing the parameters, in this case h, k and r, I can obtain so many different circles, but they will always be circles. Likewise, if you have a fixed shape, always you can write an equation. We call it in general a parametric equation. We can write a parametric equation to give a family of fixed shapes. So the answer for point number 2 is yes, we agree. Always we can write a family of fixed shapes using a parametric equation. Do you see the connection between statistics and mathematics? We have distributions which have fixed shapes. So the distributions always have a specific equation. Okay? That's the bottom line that I will write down under point number 2. The distributions are always fixed because we talk about the distributions of quantitative random variables. They are always fixed, therefore they must have a specific equation. Alright, let's move on to point number 3. 2 types of summary statistics. Now we try to obtain those parameters. By obtaining the parameters, I can talk about the distributions. In the previous chapter, we basically drew the distributions. Histogram was drawn, and we observed the shape of the distribution using the shape of the histogram. Now in this chapter, what we do is we try to get an analytical approach rather than just graphically seeing it. In this chapter, we try to estimate the shape of the graph using some statistics. Let's go to point number 3. 2 types of summary statistics, measures of center and measures of variability. We will revisit this one real quick. We already discussed measures of center and measures of variability, a brief discussion during our last lecture. And then we are going to use those measures of center and measures of variability in order to talk about the geometric shapes of the data, or in other words, the distributions. All right, so we said we have measures of center and measures of variability. So what are the measures of center? They tell us the overall size of the data. For example, if I talk about the weights of humans, maybe 200 pounds. And if I talk about the temperature these days, I'm talking about maybe 75. That may be a midpoint, a center. And if I talk about the jackpot of Mega Millions, it may be 40 millions. That's about the average or the center for that. That gives you the overall size, measures of center. What specific statistics will give us measures of centers? Well, the very first one is the average. We also said we call it the mean. We also have a symbol for that. Remember, what was the symbol? That was X bar. And we also have the median. What is median? Well, median means when you set all your data in the increasing or decreasing order, what comes in the exact midpoint? That's called the median. We will see the median calculation in a few minutes. And we also have a symbol for that, M and sub B. That's the median. There can be a couple more other measures of center, but average is the most important measure of center, and we will also look at the median occasionally. And of course, by comparing mean and median, we can talk about the shapes of the distributions to a great extent. We will see how it is done a little bit later. All right, and that's about the measures of center. And then we also have measures of variability. these measures quantify how distant each individual data point compared to the center. Okay. This gives us, I would say, tells how distant each data point compared to the center. For example, let's say I have a graph for the wind speeds. Let's say today I have like around 5 miles per hour. Now that's my center. And then each data point will be very close to the center, but they're not necessarily be exactly on the center line. They'll be somewhere around, somewhere close, like this. Now that's the variability. So each data point, how far is it from the center? That should be given by the measures of variability. So one simple measure of variability is the range. Range is defined as the maximum minus minimum. So this definition of range is different from college algebra definition of range, which is used for the functions. In statistics, we define it as maximum minus minimum. And there are a few other things also discussed under measures of variability. I will just give you the names of those quantities at this point of time, and we will see what are those measures of variability a little bit later. So other variables are the variance and standard deviation. So range is one measure of variability, and variance is one measure of variability, and standard deviation is another measure of variability. And there are some others, such as the quartiles. The first quartile, second quartile, the third quartile, and so on. So the quartiles are also classified as measures of variability. And in the future, you will see second quartile is also equal to the median. Therefore, median is kind of like classified under both measures of center as well as measures of variability. And there are a few other measures of variability, such as mean absolute deviation and so on. But for us, we will just look at these things. Of course, mean absolute deviation is not a very highly used measure of variability. So we'll just focus on these things. All right, so those are the measures of center and measures of variability. Let's move on to the next point, importance of summary statistics. Now these are called summary statistics. Okay, these are measures of center. These two are summary statistics. I gave you the symbols used for average and median. I didn't give you the symbols used for measures of variability, so I will write them down. The variance is usually given as S squared. That's the variance. Standard deviation is given as S. That's because we take the square root of the variance for the standard deviation. The quartiles, even though there are 4 quartiles, we will just look at 3 points that will define the starting or ending points of the quartiles. They're called Q1, Q2, and Q3. Now, importance of statistics. Well, importance of reporting both types of statistics. That title under point number 4 should be written actually as that. If you report measures of center alone, that may not be enough. You will also have to report measures of variability. On the other hand, just reporting measures of variability alone will not be enough. You will also have to report measures of center. Simply speaking, the purpose of statistics, purpose of calculating these values is actually to replace a huge pile of data. To replace a huge pile of data, I cannot go ahead and simply write down the average or the median alone. I cannot simply go ahead and write down 1 or 2 of the measures of variability, and then I cannot discard my data set. Before discarding a data set, I need to make sure that at least one measure of center was calculated. At least one measure of variability was calculated. And we must report both of them, otherwise we are not giving a proper summary. Why is that? Let's look at the two data sets given under point number 4. You have data set 1 and data set 2. Now calculate the mean for the data set 1 and the mean for the data set 2 respectively. You already know how to calculate using our TI-84 calculator. So enter data set 1 into list L1 and enter the data set 2 into list L2. And then calculate the summary statistics for data set 1 and data set 2 respectively. Alright, let's go to the calculator.
Here's your TI-84 CE+ calculator. First, we will enter the two sets of data into this calculator. How do you enter? You have to go to Stat, Edit, number 1 Edit, Enter, and then you can see the lists. We will enter dataset 1 into list L1 and dataset 2 into list L2. To save some time, I have previously entered the two sets of data into L1 and L2 respectively. And now I have to run descriptive statistics. You already know how to run descriptive statistics for a given variable. Let's say I need to run descriptive statistics for the data points in list L1. All I have to do is to hit Stat, select Calc by pressing the right arrow key, and then select number 1 variable stats, hit Enter, and then you can define the list is L1 because that's where I have dataset 1. And if I need to calculate the descriptive statistics for dataset 2, I have to change the list into L2, which is second and 2. And then we can simply select Calculate. It will calculate the descriptive statistics for the second variable. But this dataset is slightly different. If we go back and see the dataset that we have already entered, both datasets have the same number of data points. First dataset has 7 data points, and the second dataset also has 7 data points. In that case, you actually don't have to calculate descriptive statistics in 2 different steps. We can calculate descriptive statistics for data in L1 and L2 separately in single setting. All we have to do is to define the list L1 as variable X and list L2 as variable Y. Then calculator will calculate all the descriptive statistics of X and all the descriptive statistics of Y separately. It will give us all those calculated statistics in a single output screen. So let's do it that way. Stat and Calc, and then you can select number 2 variable stats. Hit Enter, and now I have to define X list and Y list. I have entered the first dataset into list L1, so I will define it as that, second and 1, that is L1. The Y list is L2. To define it as that, you have to press second and number 2. There is no frequency list. Skip that and select Calculate and then hit Enter. Now this will calculate all the distributed statistics for 2 sets of data separately. You can see that the first half corresponds to all the X values, which means dataset 1. X bar stands for the sample mean, which is equal to 50. And you know all the other statistics. SX stands for the sample standard deviation. And if you go down, you can see Y bar, that is the mean of the second dataset, which is also equal to 50. And if you scroll down, as the last part of the output, you can see minimum X, minimum Y, and maximum Y. Remember one additional point. You cannot calculate descriptive statistics for both variables unless you have the same number of data points for L1 and L2.
All right, now you can see for dataset 1, the mean was found to be equal to 50, right? And for dataset 2, once again you can see that the mean is equal to 50. But if you carefully see this dataset, the 2 datasets of course, the first dataset, every single data point is very close to 50. In the second dataset, all the data points are actually different from 50. The average is still 50. Can I just report these measures of center and discard the two sets of data. No, I should not do that, because unless I see the two data sets separately, I might assume that data set 1 is equal to data set 2 just by looking at the two means, because the two means are equal. Now that explains why just one measure of center or measure of variability is not going to be enough. So we will also calculate at least one measure of variability. At this point of time, what we can easily calculate is the range. We know the maximum and we know the minimum, and then we can take the difference and calculate range. So let's calculate range for the first data set and range for the second data set. So what's the range for first data set? What's the maximum for first data set? I think the maximum is 50.2 and the minimum is 49.8. So the range should be 50.2 minus 49.8, which simplifies to 0.4. That's the range for the first data set. The same way we can calculate the range for the second data set. For the second data set, I think the largest is 100 and the smallest is 20. Therefore, the range is 80 for the second data set. Now, by looking at these two types of summary statistics, we can clearly figure out that the first data set is different from the second data set, even without looking at the individual data points any longer. Right? So that's how it is important to report at least one measure of center and at least one measure of variability when reporting summary statistics for a data set. Of course, one measure of variability is usually not enough. We will go for at least two measures of variability. And as measure of center, usually the mean is recognized as a really strong character, but we usually provide both of these values. And then equations for measures of center, mean and median. I think on the first day itself, we already saw the equation for measures of center, the mean. Remember? How do we calculate the mean? The mean is calculated by adding the data and by dividing the summation by the number of data points. So how did we write down that equation? Can you remember that we used a symbol for the summation? What was that symbol? The symbol that we used for summation is sigma. If the variable was labeled as x, this represents the summation of all the data points. And I'm going to divide that by n, where n is the sample size. So this gives us the sample mean, or the average. So I will define these things first. So I will let x be a random variable. Now this random variable could be temperature, wind speed, air pressure, blood pressure, anything as such. Tensile strength of something, aluminum alloys, the thermal conductivity of copper, or electrical conductivity of some material, and so on. So that variable is labeled as x. And then we will let x bar be the average, or the mean. So here's the definition. Here's the equation for the mean, calculation of the mean. So this is the summation of x and n is the sample size. I would say n be the sample size. So sigma x, we already know, it represents the summation of all the data points of the variable x. We already saw this equation, and that's the first equation you will see in this class. And we are not going to use this equation as an equation because we will always use technology to do all our calculations. And then I need an equation for the median. Well, of course, there is no specific equation for the median. there are instructions to calculate the median if you want to calculate by hand, but we will never calculate by hand. But there's a way to calculate it, and I'm going to explain it, and this is how your calculator or MS Excel calculate the median. So you will need to arrange the data set in the ascending order or the descending order. Either of the two orders is fine. Arrange the data in the ascending or descending order. And then you pick the midpoint. And if you have more than one midpoint, take the average of the two midpoints. If more than one midpoint exists, take the average of the two midpoints. Say for example, I went outside and found the temperature readings. So the first reading was 75. The second reading was found to be 70. Well, the second reading is smaller than the first reading, so I will write it still here because I need to first write them in the ascending or descending order. I prefer the ascending order. Okay. Let's say the third reading was 77, and I got another reading. Well, not yet. Now, if I need to calculate the median now, the median is this one. Arranged in the increasing order, pick the midpoint. To the left, I have one data point. To the right, I have one data point. Therefore, 75 is the median. And let's say I picked another temperature reading, and it was found to be 79. Now, what's the median? So the median is I have two data points in the middle. I have to take the average between those two. So the average will be 76. 75 plus 77 divided by 2, which is 76. So median will be 76. Now this is not a data point present in the data set, but it's a value that's calculated based on the data set. Anyways, this is the first time you see the equation in this class, and I mean the steps of calculating the median. And also this is the last time we will discuss the steps of calculating the median, because we will use technology to calculate the median. Now we go to point number 6, equations for the measures of variability, range, quartiles, variance, and standard deviation. For variability. The range we already saw. What's the equation for range? We defined range as maximum minus minimum. So observe your data set and pick the maximum and pick the minimum and take the difference. That should give you the range. So it's as simple as that. And then quartiles. To find quartiles, we have to do something. First, you have to arrange the data in the increasing order or the ascending order. Unlike the median, you cannot do it in either of the two orders, not ascending or descending. For quartiles, you should arrange the data only in the ascending order. And again, we are not going to do this by hand. We have technology, but I just want to show you how your calculator and MS Excel do the calculations for quartiles. So the first thing is arrange the data in the ascending order, increasing order. And the target for quartiles is, you will see, here's my data set, and here's the minimum, and here's the maximum. Of course, range is the difference between the two. And in quartiles, I need to find 3 points One point will be the midpoint. And that midpoint is called Q2. So the median of the data, we already know how to find the median. Okay? The median is called the second quartile. Median is called Q2. Once Q2 is found, what we then do is just look at the first part of the data set alone, and then find the median for that part of the data set. That median is called the first quartile, written as Q1. So I write it as that. For the first half of the data set, find median. It will be equal to Q1. Of course, we say the first quartile is all the numbers from minimum to this point. And Q1 stands for the end point of the first quartile. And we say the second quartile is this. All the numbers between these two. And this end point is called Q2. And the same way, if you find the median for the upper half, you will have Q3. Okay? Median for upper half is equal to Q3. And in your calculator, you can easily find Q1, Q2, and Q3 in the output for one variable statistics. All right, so that's how we calculate the quartiles. And then we would like to calculate the variance. So the variability was defined as the distance of each data point with respect to the center. We can use this definition and come up with another measure of variability. Let's see how to do it. So the third type under the variability is variance. It's called variance because the basic definition of variability is used to define the equation of the variance. We know the center is, the best estimate for center is x bar, right? Now data points can be written as x1, x2, x3, x4, up to, let's say, xn. Now what's the distance, relative distance to the center from each data point? From x1, let's say it's x1 minus x bar. From x2, it'll be x2 minus x bar. From x3, it'll be x3 minus x bar. From x4, it'll be x4 minus x bar, and so on. From xn, it'll be xn minus x bar. Right? Now remember one thing. When we say measure of center, the center will be somewhere here. This is center, which is x bar. The other data points will be around that center. When I say around that center, about half of the data points will be larger than the center. About another half of the data will be lesser than the center. But when I follow this strict definition, then I have, what I did was, I subtracted x bar, which is the center. Now we know some data points are larger than the center. The other data points are smaller than the center. But no matter what, I consistently subtracted mean from every single data point. That means about half of this will be negative. About half of that will be positive. Now I also need to find an average distance. Now in order to find the average distance, if I go ahead and add these differences and divide by the number of differences I have, that will not give me a good estimate, because some are positive, the others are negative, they will be cancelled with each other if I directly add these values. That will not help us to find the variance. So what we do is, for variance, we square these things. Each difference is squared. When you square them, they all become positive. So x1 minus x bar is squared. And then I can add x2 minus x bar is squared. Then x3 minus x bar is squared. Plus x4 minus x bar squared. Up to xn minus x bar squared. And then what we do is, we can divide this by n. But instead of dividing it by n, we divide it by n minus 1. Why is that? Well, now here's the argument. This has a serious reason called the estimator being unbiased. That's advanced statistics. At this introstat level, this is how I can explain this. Instead of dividing by n, why we divide by n minus 1. If I have just one data point, it will be the measure of center. Can I consider that data point itself as the variability as well? No. Think about that data set 1 you found on page 1. Data set 1 had all the data points very close to 50. And let's say instead of all these data points, I had just one data point which says, let's say the first data point, 49.1. I have only that data point. I have to take it as measure of center, not as a measure of variability. Of course, if I take that data point as measure of center as well as the measure of variability, and then I'm in real trouble because I'm totally misinterpreting the data set. The measure of variability is never 49.9 for that data set 1. So, when you have just one data point, we say we cannot calculate variability. In order to calculate variability, you need at least 2 data points. So, we have an equation which will give you an undefined form if your n, or the number of data points, is equal to 1. If your n is equal to 1, you are dividing by 0, right? Which is undefined in mathematics. So, in order to define this equation, I need n to be larger than or equal to 2. At least it should be 2. So, I can explain division by n minus 1 as that at intro statistics level. More explanations can be given for that at advanced statistics classes. You will see them if you are going to take advanced statistics at some point. Remember, because of these squares and because of they are sums, we take the summation. This is called s squared. This is given as s squared. And now there's another little weakness of variance when you define it this way. The data are all first order. x1, x2, x3, those are the data points. But if you look at this equation for variance, I have squared the differences. So the variability is given in squared units. But I would like to have a measure of variability with units consistent of the units of the original data. So what we do is, we take the square root of the variance. The square root of the variance is called the standard deviation. Which is square root of the variance. Okay, you can write it that way, or you can write it as square root. I will write it in words, square root of the variance. Standard deviation, the standard symbol used is S for standard deviation. Alright, so those are the equations for the measures of variability. Let's move on to point number 7, advantages and disadvantages of measures of center. So measures of center, we have mean and median. So this is under point number, is that 7? Yes. Now what are the advantages? advantage of mean, it actually uses all the data points that we collected. It's a very strong advantage that mean has over median. Okay? Uses all the data points. Sometimes the data points are expensive. Collecting one data point may take time and money. So mean, that's the justification. It uses all the data points to calculate. All right. On the other hand, median does not use all the data points. So that itself becomes a disadvantage for median. Okay? It does not use all the data points. Okay, now look at the disadvantage and advantage of these other two. So what are the advantages of median? Let's say I have a data set like this. 23.5 and 24.6, 25.1, 22.9, 23.4, 25.6 and 24.3. Look, when I wrote down this data set, I forgot to put the decimal here. I forgot that. And often it is not the person who collects the data that analyzes them. A professional statistician will analyze the data that someone else collected. And often the data are automatically imported to whatever your software. So you don't even see them. You calculate the mean for this data set. If you calculate the mean for this data set, the mean will be highly affected by this extreme outlier, right? One data point is 256. All the other data points are 23.5, 24.5, 25.1, and that kind of data points. But there is one data point which is 256, just because the person who recorded the data forgot to put this decimal. But my mean will affect because of this outlier. Okay? It's a disadvantage of the mean. So we write it down as that. Affected by extreme observations. These kind of observations are called outliers. So they are affected by outliers. Now this is a high outlier. Similarly, it will be affected by low outliers as well. And on the other hand, the median does not have this weakness, because when you find the median, you arrange all the data in the ascending order. And then these kind of outliers will always come at the beginning of the data set or at the end of the data set. If it's a large outlier, it will be the last data point. If it's a small outlier, it will be the first data point. And median will never pick those starting points or the end points. It will only pick the midpoint. So it is not affected by outliers, not affected by outliers. So that's an advantage of the median. All right, similarly, you can answer point number 8, advantages and disadvantages of the measures of variability. How about the range and the quartiles? Range and the quartiles have the same disadvantage of not using all the data points. Range has an additional disadvantage because the range is equal to maximum minus minimum. So if you have outliers in your data set, the range will directly be affected. But on the other hand, quartiles will not be affected by outliers. Quartiles are also like median. Median is, of course, the second quartile. And then for the first half of the data set, we find the median, that's Q1. For the second half of the data set, we find the median, that's called Q3. Okay? So the quartiles are not affected by extreme observations. That's an advantage of quartiles. So does range have any advantages? Well, it is very easy to calculate. And if your data set is filtered, which means if your data set does not contain any outliers, range is very strong. It quickly gives you an estimate of the variability without any hard calculations. All right, and then variance and standard deviation. Variance and standard deviation have advantages rather than disadvantages. Variance and standard deviation, they both use all the data points in the data set to calculate. And that's a very strong advantage. The disadvantage, once again, is that they are both affected by the extreme outliers. So we saw this problem of outliers. And if you can actually filter out outliers, that's the best thing that you can do before analyzing the data. We'll go to that point in a minute. But before moving into that, let's look at point number 9. Describing the shape of the distribution using the mean and the median. Of course, the purpose of calculating all the measures of center and measures of variability is because I need to describe the distributions. Right? That was the title of the chapter. Chapter 2, we said describing distributions using numbers. Now, those numbers are the measures of center and measures of variability. So how can we use those numbers in order to talk about the distributions? First comparison is between mean and median. If your mean is equal to median, then we say that your distribution is symmetric. In your lecture note, I have selected the symmetric bell curve. So if you have a symmetric distribution like that, symmetric means you have a center point, and if you fold it around the center, the two halves will nicely overlap. For this distribution, I can say mean equals median. And if your mean is larger than the median, that means median is somewhere here, and your mean will be somewhere here. So mean is larger than the median. So if your mean is larger than the median, you can see that your distribution is skewed. And it is skewed, we say, when you have a tail towards right-hand side, we say it is skewed to the right. For this case, we say skewed to the right. Skewed to the right. And on the other hand, if you have a distribution like this, your median will be somewhere here, and your mean will be somewhere here. This is because when you have an extreme outlier, the mean is affected. This happens when you have an extremely large data point. When you have an extremely large data point, mean will be dragged towards that. Median stays as it was in the beginning, okay? So median will not be affected by the extreme. So when that happens, we say the distribution is skewed to the right. Now, opposite happens here. If you have a really small data point, the median stays where it should be, but mean will be affected. So in this case, your mean is smaller than the median. Then we say your distribution is skewed to the left. That means there is a tail towards left. Okay? Now, skewed left and skewed right also have two other words. When you say skewed left, it is also called skewed negatively. When you say skewed to the right, they also call it skewed positively. Now we can move on to point number 10. Article in Quality Engineering 1992 presents viscosity data from a batch chemical process. The data set is given below. Now you have to determine if the distribution should be symmetric skewed to the right or skewed to the left using this data set. This question is extremely important. You will see a question similar to this one in your exam 1. I will give you a data set and I will ask you to determine whether your distribution is symmetric, skewed to the left or skewed to the right. All you have to do is to calculate mean and median and compare them. If they are equal, you say it is symmetric. Say for example, if your mean is equal to 50 and if your median is equal to 40. In this case, what should be the shape of your distribution? Mean is larger, median is smaller. When the mean is larger, the distribution should be skewed to the right. Okay? All right, we will do this calculation for this data set. We will first enter the data set and then do the calculation. Let's do that.
So here's our TI-84C E+ calculator, and we have done descriptive statistics calculations several times by this point, and I'm going to show you it for one last time. So this is how, once again, you calculate descriptive statistics for a given data set. First, you have to enter the given data set into the calculator. To enter the data set, you have to go to Stat, Edit, number 1, Edit, hit Enter, and then you can enter the given data set into one of these lists. So I have already entered the complete data set into list L1. After entering the data, then you have to calculate the descriptive statistics. To calculate descriptive statistics, you have to go back to Stat, select Calc, select number 1, variable stats, hit Enter, and here you have to define the list where you entered your data. I have entered the data into the list L1. There's no frequency list. We skip that and then select Calculate and then hit Enter. You can see that the sample mean X bar is equal to 14.77 approximately. And if you go down, you can see that the median is equal to 14.7. Now, because the mean X bar is 14.77 approximately, and the median is 14.7, I would say that mean and median are approximately equal to each other. That means the distribution should be approximately symmetric. However, on the other hand, if somebody wants to round the sample mean X bar into the first decimal, it will be equal to 14.8. In that case, the student can argue that the mean is larger than the median. Then they can say that the distribution is skewed to the right. I will accept both answers as long as the students have justified their conclusion.
All right, let's move on to point number 11. In point number 9, we discussed how to compare the mean and median and talk about the shape of the distribution. Well, mean and median are both measures of center. We also calculated measures of variability. So we will now see how to use measures of variability to talk about the shapes of the distributions. That's given under point number 11. You can calculate the variance. Now, if this distribution has a certain variance, a more spread out distribution means larger variance. Okay. So, let's say, for example, variance of this distribution could be, let's say, 10. The variance of the red distribution here should be larger because it's more spread out compared to the center. It's more spread out compared to the center and compared to the distribution given in blue. So this variance may be 13. And if I have another distribution like this, you can see most of the data points are very close to the center. That means this distribution must have a smaller variance than the distribution given from blue. In fact, it should have the smallest variance. So that variance may be, let's say, equal to 7. Now, a more generalized case is given in the diagram. Let's go for point number 12, checking for the outliers. We said we have the mean and the median as measures of center. And we said we have variance, the standard deviation, and a couple other things as the measures of variability. only measure of center which uses every single data point in my data set is the mean or the average. And we have two measures of variability which use all the data points in my data set. Those are the variance and the standard deviation. But the mean or the average, as well as the variance and the standard deviation, are affected by extreme outliers. Now, any measure that uses all the data points will always be affected by outliers. Now, that's not good. If you have an outlier in your data set, most probably it's a recording error. I must have a natural upper limit and a natural lower limit. And if any data point is going to go outside of those two limits, I can classify them as high outliers or the low outliers. Now, once the outliers are identified, I can either filter them out, or I can see if I can fix those outliers with their correct values. And then we can do all the calculations, such as the mean and the variance and the standard deviations. So if your data set technically does not have any of the outliers, mean will be the best measure of center. The standard deviation and the variance will be the best measures of variability, because they use all the data points. So we will first see how to figure out the outliers in a data set. Now, to determine the outliers, we will need the quartiles. You already know how to calculate the quartiles, Q1, Q2, and Q3, using your calculator, as well as we can use MS Excel. So we need Q1, Q2, and Q3. I'm working on point number 12, checking for outliers. As the first step, we will calculate something called the interquartile range, which is abbreviated IQR, interquartile range. This is defined as Q3 minus Q1. And then we define the lower limit. So here's the lower limit. Lower limit is equal to Q1 minus 1.5 times interquartile range. Q1 minus 1.5 times interquartile range. Now this is a lower limit. Your calculator does not have this equation. So this is one equation you will have to remember for this class, for the exams. Now, once this lower limit is calculated, if your data set contains any data points that are smaller than this lower limit, those data points are called low outliers. Similarly, we can calculate an upper limit. Upper limit equation is Q3 plus 1.5 times interquartile range. And any data set in your data set which is larger than the upper limit will be classified as a high outlier. Okay? So I will write it down. Any data point smaller than lower limit is a low outlier. Any data point larger than the upper limit is a high outlier. Your first exam will ask you to calculate these two limits. And I will also give you a data set, and then you can see if there are any data points that are smaller than the lower limit and that are larger than the upper limit. Such data are classified as outliers. Calculation of the outliers will be a very important step in analyzing the data. Okay, that's actually the very first step of analyzing data. And any graphical representations and any calculations of measures of center and measures of variability actually are done after filtering your dataset for outliers. All right, let's move on to the next point. Point number 13, the 5-number summary. Well, the 5-number summary is there are a couple of 5-number summaries. The first 5-number summary is the minimum of the dataset, the first quartile of the dataset, median of the dataset, third quartile of the dataset, and the maximum of the dataset. That's the first 5-number summary. And there's another 5-number summary defined. It'll have these 3 middle pieces, but the minimum is replaced with the lower limit. What's the lower limit? The lower limit is the lower limit calculated by this equation. And you have the same Q1, median, Q3, and the 5th is, instead of the maximum, you write the upper limit. So they are both used as 5-number summaries in various different textbooks. They both can be accepted. And then under point number 14 and 15, we have box plots. Corresponding to each of the 2 5-number summaries, we can draw box plots. Now what's a box plot? The box plot is something like this. So the box plot number 1, which is for point number 14, is something like this, and this point is the minimum, and this is Q1, and you will also show the median. This is Q3, and this is your maximum. And you don't write these things in words. You can draw it like that and write down the exact values. Okay? At these points, you should write down the values. Of course, we will not draw the box plot by hand. Instead, we can use MS Excel to draw the box plot. And it should be drawn to a scale. So these lengths will be determined according to that scale. This is also called box whisker plot. Now, here's the big box, and these are the 2 whiskers. We can use box whisker plot and see if your distribution is symmetric and so on. Of course, if you have a box plot which is symmetric around the median, these 2 lengths are equal to each other. In that case, your distribution is symmetric. So this is your first box whisker plot for this 5-number summary. And then box whisker plot number 2, which is also the box whisker plot given by MS Excel, is this. You have a similar representation, but this time, instead of the minimum and maximum, we have the lower limit, Q1, median, Q3, and upper limit. Now, one special characteristic of this box whisker plot is if you have any outliers, they are also shown outside of the lower limit and the upper limit. Let's say I have 2 high outliers. They are shown like this, little stars. And if I have 1 low outlier, it will be shown like that. So this is the second box whisker plot, and this is what you will get from MS Excel. So we saw the equations to calculate the lower limit, the upper limit, and now we are all set to go into point number 16. Now you have a data set. Please go ahead and read the given details of that yourself. We have to determine if there are any outliers in the data set. Okay? So, first thing is we have to enter this data set into your calculator. And then you have to find Q1 and Q3. And then you have to use those equations and determine if there are any outliers. All right, do it yourself. Let's move on to point number 17. The box whisker plot for the data in question number 16. The point number 16, we had a data set and it shows you the box whisker plot for that. Now here's the box whisker plot. And MS Excel, this is an output taken from MS Excel. Now that output actually doesn't have any outliers, okay? that also says that our data set doesn't have any outliers. So it confirms whatever the result that we obtained in the previous step. This box whisker plot can be drawn horizontally or it can be drawn vertically, no problem. All right, and there are some comments on box whisker plot. If you have a longer upper whisker, if this whisker is longer compared to the other one, this is called the upper whisker, this is called the lower whisker. One in the right hand side is the upper whisker. If it is longer, then we say that the distribution is skewed to the right. And if you have a longer lower whisker, then we say, if this is longer, then we say that the distribution is skewed to the left. And if the box whisker plot is about symmetric, approximately, then we say that the distribution is also symmetric. When we say symmetric and skewed to the right and skewed to the left, it doesn't necessarily have to be that bell curve. Okay? Anything symmetric is symmetric. For example, a rectangular distribution is also symmetric. When a rectangular distribution is skewed, it looks a little bit ugly and it's a bit difficult to understand. So that's why I specifically picked that normal bell curve. And of course, in the future, we're going to repeatedly use the normal distribution, which is that nice symmetric bell curve. All right, and then on the point number 19, how to deal with outliers in a data set. Often, the outliers are typos, and we have to see if those can be corrected. The person who corrected the data should be often contacted and see if he has some other records and see if it can be corrected. Sometimes the person who collected the data may be not available any longer in that institution. He may have left that place and there's no way you can verify the data. In such situations, maybe we have to see if we can discard the data point or if we can collect the data point again. So the summary statistics calculated using a filtered data set, this is under point number 20. Those statistics are called trimmed statistics. Let's say I had 2 high outliers and 1 low outlier. I dropped all 3 data points from my data set. Now I calculate the mean. That mean is called trimmed mean. I calculated the variance for the filtered data set. It's called the trimmed variance. And so on. All right, so that's it for the class of today. Thanks.